Tonight we're going to answer a question that turns out to be more complicated than it sounds, and more interesting than most science communication has conveyed. How fast is the universe actually expanding right now? Before we get started, if you love exploring the deep mysteries of our universe as much as we do, take a second to subscribe or like the video. It helps this channel reach more curious minds like yours. Now, let's begin. The answer that most sources give you is somewhere between 42 and 45 miles per second per megaparsec, meaning that for every 3.226 million light years of distance, galaxies are receding from us at an additional 42 to 45 miles per second, and they usually say this as if it were a settled fact with a small measurement uncertainty. But one of the most significant scientific controversies of the last decade is the fact that those two values represent two completely different measurement methods that are not converging on the same answer, and the gap between them is now large enough that many cosmologists believe it reflects new physics that we do not yet understand. To understand why that gap matters, we first need to understand what the expansion of the universe actually is, because most intuitions about it are wrong in important ways. The universe is not expanding in the sense that galaxies are moving through space away from each other, like fragments from an explosion flying outward through a pre-existing void. Space itself is expanding. The distance between any 2 points that are not gravitationally bound to each other increases over time, not because those points are moving through space, but because the space between them is growing. The galaxies are, in a meaningful sense, sitting still while the ruler between them gets longer. The balloon analogy helps and misleads in roughly equal measure. Imagine dots drawn on the surface of an inflating balloon. As the balloon expands, every dot moves away from every other dot, and the recession speed depends on how far apart the dots are. 2 dots close together move apart slowly. 2 dots on opposite sides of the balloon move apart quickly. There is no center to the expansion. Every dot can consider itself the center, because from every dot's perspective, everything else is receding. The analogy misleads because the balloon has a center in 3 dimensions. The point inside the balloon where the air goes, and the universe does not have a corresponding center in 4-dimensional spacetime. The universe is the surface of the balloon without the balloon's interior. The expansion is in the fabric itself, not into anything outside it. The rate of this expansion is described by the Hubble constant, named for Edwin Hubble, but based on work by multiple astronomers across several decades. The Hubble constant tells you how fast a galaxy is receding from us for every unit of distance. A galaxy that is 1 megaparsec away, about 3.226 million light years, is receding from us at a rate given by the Hubble constant in miles per second. A galaxy twice as far away is receding twice as fast. The relationship between distance and recession velocity is linear, and the Hubble constant is the slope of that line. What makes the Hubble constant strange and important is that it is not actually constant over time. It changes as the universe evolves. What we call the Hubble constant is really the Hubble parameter evaluated at the current moment in cosmic history, and astronomers denote it h, naught to indicate that it is the present day value. At earlier times in the universe's history, the expansion rate was different, in some epochs faster and in others slower, and tracking that history is one of the main ways we understand the universe's content and fate. By the end of tonight, we will understand exactly what the two competing measurements are, why they disagree, what it would mean if neither measurement is wrong, and what the expansion rate tells us about the past and future of everything that exists. One of the most anticipated tests of the Hubble tension came from the James Webb Space Telescope, which launched in December 2021 and began scientific operations in mid-2022. Webb was expected by many cosmologists to potentially resolve the tension, or at least identify whether systematic errors in the Hubble Space Telescope's Cepheid measurements were responsible for the discrepancy. Here is what actually happened, and no one expected it to go quite this way. The Cepheid base distance ladder has a known potential vulnerability. Cepheid stars in distant galaxies are measured against a backdrop of other stars, and in crowded regions near a galaxy's centre, multiple star images can overlap, a problem called crowding or blending. If a faint background star is blended with a Cepheid, the Cepheid appears brighter than it actually is, making it seem closer than it truly is. This would cause the distance ladder to underestimate distances and therefore overestimate the expansion rate, which is exactly the direction of the discrepancy. The hypothesis was that Hubble Space Telescope, with its resolution, might be systematically suffering from blending errors. Webb's significantly sharper infrared vision was supposed to separate these confused stars and reveal whether blending was inflating the Hubble constant estimate. The SHOES team conducted an extensive Webb-based Cepheid program in 2022 and 2023, measuring Cepheid variables in nearby anchor galaxies with Webb's resolution and comparing the results to prior Hubble observations. The results, published in early 2023, confirmed the high local value with Webb's data. The Cepheid distances from Webb agreed with Hubble's measurements. Crowding was not the dominant source of error. The SHOES team's high local value survived the scrutiny of the most powerful space telescope ever built. No one predicts this means the distance ladder is perfect, and the tension is definitely real new physics. There are still potential systematic effects being investigated. The calibration of the Cepheid period, luminosity relation depends on how it is measured in the Large Magellanic Cloud. The nearest galaxy where individual Cepheids can be individually resolved and studied with high precision. Any error in that calibration propagates through the entire distance ladder. But the LMC calibration has also been scrutinized extensively, using independent methods including detached eclipsing binaries, which measure distances using only stellar physics and no distance ladder assumptions, and those measurements support the Cepheid calibration. Webb also provided an important second result, an independent measurement of the Hubble constant using gravitational lenses. The time-delay cosmography method, pioneered by the Astrophysical Collaboration and now pursued by the TD-Cosmo team, measures the time delays between multiple images of the same quasar as its light travels around a foreground galaxy. The delay between the images depends on the geometry of the gravitational lens, which in turn depends on the Hubble constant. TD-Cosmo's measurements give a Hubble constant of approximately 73.3, consistent with the SHOES value and not with the Planck value. 3 independent probes of the local universe, the Cepheid distance ladder, the time, delay cosmography from gravitational lenses, and a third method using surface brightness fluctuations in elliptical galaxies all give values around 45 miles per second per megaparsec. The cosmic microwave background gives approximately 42. Something in this picture must change, and the longer both sides of the tension hold firm, the more seriously the physics community is taking the possibility that the answer is not a correction to any existing measurement, but new physics that none of the current models contain. The story of how we learned the universe was expanding at all begins in the early 20th century, when astronomers were still debating whether the Milky Way was the entire universe or just one island in a much larger cosmos. The key figure before Hubble was Henrietta Swan Leavitt, an astronomer working at the Harvard College Observatory in the early 1900s. Leavitt was assigned to measure the brightness of stars from photographic plates, painstaking work that was considered too routine for the male astronomers at the institution. In 1908, and more fully in 1912, she published a finding that would underpin all of modern cosmology. Certain pulsating stars called Cepheid variables had a precise and predictable relationship between their period of pulsation and their intrinsic luminosity. Brighter Cepheids pulsated more slowly. Dimmer ones pulsated faster. If you watched a Cepheid variable for long enough to measure its period, you knew its true luminosity. If you knew its true luminosity and could measure how bright it appeared in the sky, you could calculate how far away it was. Leavitt had discovered what astronomers call a standard candle, an object whose true brightness is known, so that its apparent brightness can be used to calculate distance. The distance ladder, the sequence of techniques by which astronomers measure ever greater cosmic distances, has its first rung in her work. Edwin Hubble used Cepheid variables in the 1920s to measure the distance to what was then called the Andromeda Nebula, an object that had long been debated as either a nearby gas cloud or a distant island of stars. Hubble found that the Cepheids in Andromeda were so faint that the nebula had to be roughly 1 million light years away, far outside any plausible extent of the Milky Way. He confirmed that Andromeda was a separate galaxy, and went on to measure distances to dozens of others. But Hubble also noticed something in the spectra of these galaxies, in the specific colours of light they emitted. Almost all of them showed a redshift. The lines in their spectra were shifted toward the red end of the electromagnetic spectrum, indicating that they were moving away from us. And the relationship between redshift and distance was striking. Galaxies that were farther away showed larger redshifts. They were receding faster. In 1929, Hubble published his famous plot of galaxy recession velocities against distance. The relationship was linear, and the slope of the line was what we now call the Hubble constant. Hubble's own estimate was approximately 311 miles per second per megaparsec, an enormous overestimate compared to the modern value by a factor of roughly 7, because his distance measurements were based on calibrations that were later shown to be off by a factor of several. But the linear relationship itself, and the insight it implied about an expanding universe, was correct. What Hubble did not fully appreciate in 1929, or did not publicly articulate, was that this expansion implied something startling about the past. If every galaxy is moving away from every other galaxy, and if you ran the clock backward, all that matter would converge. There would be a time in the past when everything was compressed into a much smaller volume. The expansion is the signature of an event from which the universe emerged, what we now call the Big Bang. Though Hubble himself never used that term. The specific value of the Hubble constant determines how fast the expansion is happening today, which in turn tells us how old the universe is, how large the observable universe is, and how the expansion rate has changed over cosmic time. Getting this number right is one of the central challenges of modern cosmology, because no one expects the answer to be as stubbornly contested as it has turned out to be. To understand why the two Hubble constant measurements are so difficult to reconcile, we need to understand the distance ladder in much greater detail, because the ladder is an interdependent chain of assumptions, and each rung rests on the one below it. The distance ladder is the name astronomers give to the sequence of measurement techniques that extends from nearby objects, where multiple methods can be used and checked, to distances so great that only the most luminous objects in the universe are visible. Each rung of the ladder must be calibrated against the rung below it, and errors in any rung propagate upward to affect all subsequent distance measurements. The bottom rung is geometric parallax. For stars within a few thousand light years, astronomers can measure distances directly using the Earth's orbit as a baseline. As the Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars, a phenomenon called parallax. The amount of shift depends on the distance to the star. The Gaia satellite, launched by the European Space Agency in 2013 and operating through the 2020s, has measured parallaxes for over 1 billion stars with unprecedented precision, providing the most accurate geometric distance scale we have ever had. The second rung is Cepheid variable stars. Henrietta Leavitt's period luminosity relationship allows astronomers to measure the intrinsic brightness of a Cepheid from its pulsation period. The standard version of this calibration is anchored to Cepheids in the Large Magellanic Cloud, whose distance has been measured independently by several methods, including those precise, eclipsing binary star measurements that require no assumptions about Cepheid behavior at all. Those binary measurements give the LMC distance as about 163,000 light years, and that distance becomes the anchor for the entire Cepheid calibration. Cepheids are bright enough to be observed in galaxies tens of millions of light, years away with the Hubble Space Telescope, and now in greater detail with Webb. The SHOES team has identified and measured Cepheids in 42 anchor galaxies that host Type Ia supernovae, for which we have distance estimates from the Cepheid method and brightness measurements of the supernovae. This calibration is the bridge between the Cepheid rung and the supernova rung. Type Ia supernovae form the third rung. These explosions are produced when a white dwarf star accretes enough mass from a companion to exceed the Chandrasekhar limit, approximately 1.4 solar masses, triggering a thermonuclear runaway that destroys the star completely. Because the trigger mechanism is tied to a specific physical threshold, Type Ia supernovae have a relatively standardized peak luminosity. Corrections based on the light curve shape, specifically the speed with which the supernova brightens and fades, improve the standardization further. The corrected peak brightness of a Type Ia supernova can be predicted well enough that its distance can be inferred from its apparent brightness to about 5% accuracy for individual supernovae, and to better than 1% accuracy when hundreds of supernovae are combined statistically. Type Ia supernovae are bright enough to be observed at redshifts of 1 and beyond, corresponding to distances of billions of light years, well into the regime where the expansion velocity is dominated by the Hubble flow rather than local gravitational effects. By comparing the measured brightness and redshift of Type Ia supernovae at cosmological distances, the SHOES team can determine the ratio of recession velocity to distance, which is the Hubble constant. No one expects the calibration to be perfect. There are known potential complications. Cepheid pulsation behavior can vary with the chemical composition of the star, specifically with the abundance of elements heavier than helium, which astronomers call metallicity. Cepheids in metal, poor environments pulsate differently than those in metal, rich ones, and the metallicity correction is a source of ongoing refinement. The SHOES team has modelled this correction carefully and finds it does not significantly alter their result, but the metallicity dependence remains a topic of active research. There is also the question of whether the LMC anchor is representative. The Cepheids in the LMC may not perfectly calibrate Cepheids in the host galaxies of Type Ia supernovae if those environments differ systematically in metallicity, age distribution, or stellar density. The Webb observations are helping to address this by measuring Cepheids in environments more similar to supernova hosts with better resolution than was previously possible. A completely independent calibration of the Cepheid distance scale uses mirror variables, a different class of pulsating giant stars with their own period, luminosity relationship. Mirror. Base distances to the nearby galaxies where Cepheids are calibrated agree with the Cepheid distances, supporting the overall calibration framework. The consistency across all of these methods, Cepheids, mirrors, eclipsing binaries, surface brightness fluctuations in elliptical galaxies, and gravitational wave sirens, is why most cosmologists believe the local measurement of the Hubble constant is not simply a systematic error. The local universe appears to be expanding faster than the early universe measurement predicts, and the breadth of methods supporting the local measurement makes it harder and harder to attribute the tension to any single miscalibration. Here is the problem at the heart of modern cosmology, stated as precisely as possible. There are two fundamentally different ways to measure the Hubble constant, and they give systematically different answers. The gap between those answers has been growing larger and more statistically significant as both methods have improved, and it is now at the level where it cannot be explained by measurement error alone. Something is wrong with our current model of the universe, or there is new physics that neither measurement method accounts for. The first method is called the late universe or local measurement. It uses the distance ladder, the same chain of calibrations that began with Cepheid variables. The SHOES team, which stands for supernova H0 for the equation of state, has refined this technique over many years under the leadership of Riess at Johns Hopkins University. The team measures Cepheid variables in nearby galaxies to calibrate the distances to those galaxies. They then use those calibrated galaxies to standardize a second type of standard candle, type Ia supernovae, which are so intrinsically bright that they can be seen across billions of light years. By measuring the apparent brightness of type Ia supernovae at very large distances, and comparing that to the standardized brightness derived from the Cepheid calibration, they measure distances across the observable universe. The ratio of recession velocity to distance gives the Hubble constant. The SHOES team's current best value from 2022 is approximately 45 miles per second per megaparsec. The measurement uncertainty is small, less than 1 mile per second per megaparsec. Absolutely no one predicted, when both methods were in their early stages, that this number would end up sitting so far from the competing measurement. The second method is called the early universe measurement. It uses the cosmic microwave background, the afterglow of the Big Bang, which permeates the entire observable universe at a temperature of approximately 2.7 Kelvin. The Planck satellite, operated by the European Space Agency and completing its observations in 2013, mapped this background radiation at extraordinarily high precision. By measuring the detailed pattern of temperature variations in the cosmic microwave background, cosmologists can fit those measurements to the standard cosmological model, called lambda, CDM, and derive the Hubble constant as one of the model parameters. The Planck team's best value is approximately 42 miles per second per megaparsec, again with a small uncertainty. 42 versus 45. The discrepancy is about 8%. The uncertainties on each measurement are small enough that the two values are inconsistent at what statisticians call 5 sigma, meaning there is roughly a 1 in a million chance that both measurements are correct and the difference is just statistical noise. In particle physics, 5 sigma is the conventional threshold for declaring a discovery. In cosmology, a 5 sigma discrepancy between two well-established measurement methods is a signal that something is fundamentally wrong with either the measurements or the model. This discrepancy is called the Hubble tension. It is not a minor rounding dispute. It is one of the most important open problems in physics, because neither measurement team has been able to find a systematic error large enough to close the gap, and because closing the gap, if it cannot be done with systematic corrections, may require adding new physics to the standard cosmological model, physics that would change our understanding of what the universe contains and how it evolved. The cosmic microwave background is the other anchor of the Hubble tension, and it is worth understanding in detail both because it is one of the most extraordinary observations in science, and because the way it yields a Hubble constant is completely unlike the distance ladder approach. The cosmic microwave background, or CMB, is the oldest light we can observe. In the first moments after the Big Bang, the universe was extraordinarily hot and dense, filled with a plasma of free electrons and protons so tightly packed that photons could not travel freely. They scattered off electrons constantly, like light bouncing off fog. The universe was opaque. This state lasted for about 380,000 years. Then, as the universe expanded and cooled to roughly 3000 Kelvin, electrons and protons combined to form neutral hydrogen atoms. The universe became transparent almost overnight in cosmic terms. Photons that had previously been trapped in the plasma were suddenly free to travel. That light has been traveling ever since, across 13.8 billion years of cosmic expansion. The expansion has stretched its wavelength enormously, from the visible and near-infrared of the hot plasma into the microwave region of the electromagnetic spectrum. We detect this ancient light today as a uniform glow of microwaves coming equally from every direction in the sky, with a temperature of 2.725 Kelvin. The CMB is not perfectly uniform. There are tiny temperature variations, at the level of 1 part in 100,000, imprinted across the sky. These fluctuations are the fossil record of density variations that existed in the plasma before the universe became transparent. Slightly denser regions of the plasma were slightly hotter, and slightly underdense regions were slightly cooler. The pattern of those temperature fluctuations reflects a process called baryon acoustic oscillations, sound waves that propagated through the hot plasma during the first 380,000 years, driven by the competition between gravity pulling matter together and the pressure of radiation pushing it apart. When the universe became transparent, those oscillations froze into the distribution of matter and into the CMB temperature pattern. The specific pattern of fluctuations, analysed as a power spectrum, shows peaks at angular scales that correspond to the distances over which the sound waves travelled before the plasma froze. Those scales are set by the speed of sound in the plasma and the age of the universe at recombination, both of which depend on the detailed composition of the universe. The Planck satellite, operating from 2009 to 2013 and releasing its final data in 2018, mapped these temperature fluctuations across the entire sky with unprecedented sensitivity and angular resolution. By fitting the observed power spectrum to the predictions of the lambda CDM model, the Planck Collaboration derived the full set of cosmological parameters: the amount of ordinary matter, the amount of dark matter, the amount of dark energy, the curvature of the universe, and the Hubble constant. The best fit Planck value for the Hubble constant is approximately 42 miles per second per megaparsec. This is not a direct measurement of the current expansion rate. It is a prediction derived from fitting the early universe observations to a model. The model specifies how the universe should have evolved from the time of the CMB to the present, and what the current expansion rate should be if that model is correct. This is the critical point for understanding the Hubble tension. The Planck measurement is model-dependent. It assumes that lambda, CDM, with a cosmological constant and cold dark matter, is the correct description of the universe's evolution from 380,000 years after the Big Bang to the present day. If the universe contains any physics not included in lambda, CDM, specifically any physics that affected the expansion rate at some epoch between recombination and the present, the model prediction for the current expansion rate would be wrong even if the CMB measurements themselves are perfect. By the end of tonight, we will see that this is exactly where the most promising candidate explanations for the Hubble tension live, in the possibility that something happened to the expansion rate between the early universe and today that lambda CDM does not capture. No one expects the CMB measurement to be simply wrong. The Planck satellite data has been analysed by multiple independent teams with consistent results. The Atacama Cosmology Telescope and the South Pole Telescope, independent CMB experiments, get values consistent with Planck. The early universe measurement is robust and consistent. The tension is real, and it sits at the boundary between the two measurement regimes: the early universe, precisely mapped, and the late universe, also precisely measured, connected by a model that may be missing something. One of the most surprising consequences of the Hubble constant, and one that confuses almost everyone who first encounters it, is that the galaxies at the edge of the observable universe are receding from us faster than the speed of light. This seems to violate everything we know about physics. Einstein's special relativity establishes that nothing can travel through space faster than light. Yet the most distant galaxies are moving away from us at 2 or 3 times the speed of light. How is this possible, and is it real? The answer is that special relativity's speed limit applies to motion through space, not to the expansion of space itself. When a galaxy recedes from us because space between us is expanding, it is not moving through space in the conventional sense. The space itself is stretching. General relativity, which governs the curvature and expansion of spacetime, places no limit on how far space can expand. A galaxy can recede from us at any speed due to expansion without violating any physical law. The Hubble sphere, also called the Hubble horizon or Hubble radius, is the boundary at which recession velocity equals the speed of light. Its radius is the speed of light divided by the Hubble constant. At the current best estimate Hubble constant value, The Hubble sphere has a radius of approximately 14 billion light years. Galaxies at that distance are receding from us at exactly the speed of light. Galaxies farther away are receding faster. No one expects intuition to guide us well here. The situation gets stranger. Light from galaxies beyond the Hubble sphere can still reach us, and does. The cosmic microwave background was emitted from regions that were receding from us at about 57 times the speed of light when the light was emitted. Yet that light has travelled across the universe for 13.8 billion years, and we detect it today with our microwave telescopes. The reason is that the universe was much smaller and denser when the light was emitted, so that even though the source was receding superluminally, the light was emitted into regions that were less rapidly expanding than the source was. The light made gradual progress. The universe expanded around it, and eventually the expansion rate in the region the light was occupying slowed enough that the light began gaining ground toward us. The accelerating expansion changes this picture for the future. Objects that are currently visible to us may eventually cross a threshold beyond which no light they emit in the future will ever reach us. The observable universe is not static. It is a sphere that evolves over time, and under accelerating expansion, some objects that are currently visible will eventually fade below the event horizon of the universe, the surface beyond which no future signal can ever reach us. This cosmological event horizon is distinct from the Hubble sphere. The Hubble sphere is the current boundary where recession equals light speed. The event horizon is the boundary beyond which objects will be causally disconnected from us forever, even in principle. Under the current cosmological model with a cosmological constant, the universe's event horizon lies at approximately 16 billion light years, slightly larger than the Hubble sphere. The precise location of both of these boundaries depends on the Hubble constant. A higher constant moves the Hubble sphere closer to us, reducing the volume of space with which we can currently exchange signals. The Hubble tension, at 8%, translates to a meaningful difference in these boundaries and in the number of galaxies within our current and permanent causal reach. What this means practically is that the universe is not just expanding, it is becoming more isolated over time. The night sky in the far future will be darker not only because stars burn out, but because galaxies currently visible to us will have receded beyond the horizon of causal contact. The universe is, on the larger scales, a geometry of separation, and the Hubble constant is the rate at which that separation is growing. To understand why scientists take the Hubble tension seriously, despite the fact that 8% sounds like a small number, it helps to understand what statistical significance actually means in practice, and why 5 sigma is not just a technical threshold, but a statement about the physics being real. In any scientific measurement, there are 2 possible sources of disagreement between 2 different methods. The first is statistical noise, random fluctuations in the data that, if you made the same measurement infinitely many times, would average out to 0. The second is systematic error, a bias that pushes a measurement consistently in one direction, not because of random noise, but because of a flaw in the method, equipment, or analysis. Sigma, the Greek letter used to denote standard deviation, is a measure of how large a discrepancy is relative to the combined statistical uncertainties of the 2 measurements being compared. A sigma discrepancy is fairly common even when both measurements are correct. Statistics predicts that about 32% of measurements of the same true quantity will disagree by 1 sigma or more due to chance alone. A 3 sigma discrepancy should occur by chance only about 3 times in 1,000. A 5 sigma discrepancy should occur by chance only about 3 times in 1,000,000. The Hubble tension, at approximately 5 sigma, therefore cannot be explained by random statistical fluctuations unless we are extraordinarily unlucky. The probability that 2 correct measurements of the same quantity would differ by this much by chance is approximately 1 in 1,000,000. This is the same threshold that particle physicists use to declare a new particle has been discovered, as in the 2012 Higgs boson announcement. What 5 sigma does not rule out is systematic error. A systematic bias in either measurement, if large enough, could produce the same apparent discrepancy. This is why the scientific community has spent years searching for systematic errors in both the local measurement and the early universe measurement. Absolutely no one anticipates that this search will turn up nothing, but so far it has. The SHU's team has scrutinized their Cepheid calibration for metallicity effects, crowding effects, photometric calibration errors, and selection biases. The Planck Collaboration has checked their CMB temperature maps for foreground contamination, detector systematics, and analysis pipeline errors. The Webb telescope has independently validated the Cepheid distances, the gravitational lensing time, delay teams of independently derived values consistent with the local measurement. Multiple independent analyses of the Planck data by teams not affiliated with the collaboration have confirmed the early universe value. The systematic errors people have thought to look for are not large enough to close the gap. This is the situation that makes the Hubble tension genuinely exciting rather than merely puzzling. It is not a case where one team has a measurement and another team does not believe it. Both measurements are believed, both are well calibrated, both have been replicated by independent methods. The tension is not the product of one team being wrong. It is the product of the universe behaving in a way that the standard model does not predict. The closest historical analogy in modern physics might be the anomalous magnetic moment of the muon, a property of the muon particle that has been measured to extremely high precision and found to differ from the theoretical prediction of the standard model of particle physics by approximately 4 sigma. Like the Hubble tension, the muon anomaly is not large in absolute terms, but its statistical significance is high enough that it represents genuine new physics if the calculations and measurements are correct. Researchers are pursuing both measurements with enormous investment of time and resources, and both are expected to eventually point to physics beyond our current best models. Watching the Hubble tension unfold in real time is watching science at its best. A disagreement between careful measurements, scrutinized exhaustively, surviving every attempt to explain it away, pointing insistently towards something we have not yet understood. There is a complication in all local measurements of the Hubble constant that is worth understanding in detail because it represents a genuine source of uncertainty that the SHU's team and others have worked hard to characterize. The Hubble flow, the overall recession of galaxies due to the expansion of space, is not the only motion that galaxies have. On top of the expansion, galaxies have what are called peculiar velocities, motions produced by the gravitational pull of nearby concentrations of mass. Our own galaxy, the Milky Way, is moving through space relative to the overall Hubble flow at several hundred miles per second, pulled partly by the gravitational influence of the Andromeda Galaxy, partly by the overall pull of the local group of galaxies, and partly by the gravitational tug of larger structures at greater distances. The most significant large-scale gravitational influence on our galaxy's motion is a region of extreme mass concentration, roughly 200 to 250 million light, years away, sometimes called the Great Attractor, centered on a structure called the Shapley supercluster. The Milky Way is moving toward this region at hundreds of miles per second. Every galaxy in our local universe has a similar story. Its observed recession velocity is the sum of the Hubble flow recession and its peculiar velocity relative to that flow. Separating these two components is a non-trivial challenge. For the Hubble constant measurement, the problem is most severe at small distances. For a galaxy that is genuinely close to us, say 10 million light-years away, the Hubble flow recession might be only a few hundred miles per second, while the peculiar velocity could be a comparable or larger fraction of that total. Measuring the Hubble constant from such a nearby galaxy would give a wildly inaccurate result because the peculiar velocity contaminates the measurement substantially. No one expects this to be a simple correction. The SHU's team addresses this by measuring Hubble constant contributions only from galaxies and supernovae at distances large enough that the Hubble flow signal dominates over peculiar velocities, typically beyond about 150 million light years. At those distances, a galaxy is receding from us at thousands of miles per second due to the Hubble flow, and even a peculiar velocity of several hundred miles per second contributes only a few % contamination. Statistically, averaging over many galaxies in different directions also helps, because peculiar velocities in different regions partially cancel out. The peculiar velocity field itself has been mapped using large galaxy surveys. By measuring the velocity of thousands of galaxies and comparing those velocities to what the Hubble flow would predict for their distances, astronomers can reconstruct the gravitational field of the local universe and the peculiar velocity that each galaxy has. This reconstruction allows systematic corrections to be applied to Hubble, constant measurements made from individual galaxies or supernovae. The 2DF, SDSS LRG and QSO survey, the 60F Galaxy survey, and more recently the Sloan Digital Sky Survey's peculiar velocity catalogues have all contributed to this mapping. The Cosmic Flows project, led by Brent Tully and collaborators, has assembled the most comprehensive peculiar velocity catalogue to date, covering tens of thousands of galaxies out to several hundred million light years with distances measured using the Tully, Fisher relation and other methods. One result from peculiar velocity surveys is the direct measurement of the growth rate of large-scale structure, which describes how quickly density fluctuations in the universe are growing under gravity. The growth rate depends on the amount of matter in the universe and on the behavior of gravity. Measurements of the growth rate from peculiar velocities are in mild tension with the predictions of lambda, CDM, though the significance is lower than the Hubble tension itself. The local overdensity problem is related to peculiar velocities and is worth noting. The local universe, within a few hundred million light years of us, may be slightly underdense compared to the cosmic average. If we live in a region where the density is slightly below average, the local expansion rate might be slightly higher than the global average, a bias toward a higher Hubble constant measurement that could account for some of the discrepancy with the Planck value. Absolutely no one anticipates that a local underdensity large enough to fully explain the Hubble tension exists, because it would require an unusually large and deep void centered fortuitously on our location. The required underdensity has been constrained by galaxy surveys to be much smaller than what would be needed to close the tension, but a partial contribution from local structure is possible and remains an active area of study. The peculiar velocity challenge reminds us that measuring a universal constant from local observations requires carefully disentangling the universal signal from the local noise. The SHOES team's approach, using multiple supernovae at high enough distances that the Hubble flow dominates, is well designed to handle this challenge, but it also illustrates the depth of careful analysis that goes into a measurement that, on its surface, might seem as simple as plotting recession velocity against distance. Tonight, we should also understand that the universe's expansion rate is not fixed. It has changed over the history of the cosmos, and the discovery of how it has changed is one of the most surprising findings in the history of science. In the late 1990s, two competing teams of astronomers were using Type Ia supernovae to measure the expansion history of the universe. The Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Riess, were independently measuring supernovae at very high redshifts, billions of light years away. Their goal was to determine whether the expansion was slowing down, as gravity would be expected to cause it to do, and by how much. A precise measurement of the deceleration would tell them how much matter the universe contained, which would determine its ultimate fate. Both teams found something completely unexpected. The supernovae at the greatest distances were fainter than they should have been. Fainter meant they were farther away than expected. Farther away meant the universe had expanded more than expected since those supernovae exploded. The expansion was not decelerating, it was accelerating. No one predicted this. The discovery, published in 1998 and 1999, overturned a basic assumption of cosmology, that gravity, acting on all the matter in the universe, must be slowing the expansion over time. Something was pushing space apart faster and faster, overcoming the gravitational pull of all the matter in existence. That something was given the name dark energy, though naming it did little to explain what it is. Dark energy is now estimated to constitute about 68% of the total energy content of the universe. Ordinary matter, the atoms and molecules that make up everything we can see and touch, constitutes only about 5%. The remaining roughly 27% is dark matter, which exerts gravity but does not interact with light. The universe is, in terms of its energy budget, overwhelmingly made of things we do not understand. In the simplest model, dark energy behaves like a cosmological constant, a fixed energy density uniformly distributed through space. Einstein originally introduced a cosmological constant into his equations of general relativity in 1917 because he believed the universe was static and needed a repulsive term to prevent gravity from causing it to collapse. He later called it his greatest blunder when Hubble's observations showed the universe was expanding. But the 1998 supernova observations resurrected the cosmological constant, now understood not as a correction to a static universe, but as the dominant energy component driving its accelerating expansion. The Hubble constant is deeply connected to dark energy. The current expansion rate depends on the balance between the gravitational pull of matter and the repulsive push of dark energy. Different amounts or different behavior of dark energy would produce different current expansion rates. This is why the Hubble tension is so significant. If the discrepancy between the two measurements reflects real physics, one leading candidate for the explanation is that dark energy does not behave exactly as the cosmological constant model predicts, or that there was an additional dark energy component active in the early universe that has since faded. Either possibility would require revising what we think we know about the universe's largest scale physics. Perlmutter, Schmidt and Riess shared the 2011 Nobel Prize in Physics for the discovery of the accelerating expansion. The Hubble tension, which has grown in significance since then, may be pushing physics toward a second major revision of that already surprising picture. The type Ia supernova method is one of the most elegant tools in cosmology, and understanding it in depth helps clarify both its power and its potential vulnerabilities. A type Ia supernova is a catastrophic thermonuclear explosion of a white dwarf star. White dwarfs are the compact remnants of stars like our Sun, left behind after the Sun exhausts its nuclear fuel and expels its outer layers. A white dwarf is essentially a dead star, composed mostly of carbon and oxygen, supported against its own gravity not by nuclear burning, but by quantum mechanical pressure from electrons. The Chandrasekhar limit, derived by Subrahmanyan Chandrasekhar in 1930 when he was 19 years old, on a steamship from India to England, is the maximum mass a white dwarf can have while being supported by electron pressure, approximately 1.4 solar masses. If a white dwarf accretes material from a companion star and approaches this limit, or if two white dwarfs merge and their combined mass exceeds it, the white dwarf cannot maintain its structural integrity. It undergoes rapid carbon fusion in a runaway thermonuclear explosion that obliterates the entire star in seconds. Because the explosion is triggered by a specific physical threshold, different type Ia supernovae have similar peak luminosities. The brightest type Ia supernovae reach an intrinsic luminosity of several billion times the Sun's luminosity, bright enough to outshine the entire galaxy they occur in for a few weeks. The standardization that makes type Ia supernova useful for cosmology was worked out in the 1990s, largely through the work of Mark Phillips, who showed in 1993 that supernovae which fade quickly after peak brightness are intrinsically less luminous, while those that fade more slowly are more luminous. This width-luminosity relationship, called the Phillips relation, allows astronomers to correct the observed brightness of a Type Ia supernova for the intrinsic variation and obtain a more standardized distance estimate. Additional corrections for the color of the supernova at peak light, which indicates whether dust absorption is dimming it, further improve the standardization. By 1998, the two supernova teams had assembled enough high, redshift Type Ia supernova, observed at distances of billions of light years, to measure not just the current expansion rate, but the history of the expansion. The key quantity is the deceleration parameter, which describes whether the expansion is slowing down, staying constant, or speeding up. Both teams expected to find deceleration. Gravity acting on all the matter in the universe was expected to be braking the expansion, just as the Earth's gravity brakes a ball thrown upward. Instead, they found the opposite. The high, redshift supernovae were fainter than expected, meaning they were farther away than they would be in a decelerating universe. The universe was not slowing down. It was speeding up. Dark energy, the name given to whatever is causing this acceleration, became one of the central problems of physics overnight. The supernova method has been extensively cross-checked since 1998. The Supernova Legacy Survey, the Essence Survey and the Dark Energy Survey have each assembled samples of hundreds of Type Ia supernovae at high redshift. All confirm the accelerating expansion. The systematic errors have been scrutinized. Dust contamination, evolution in supernova properties with redshift, selection biases in the samples and contamination from other supernova types have all been modelled and found to be insufficient to eliminate the dark energy signal. But the question of Type Ia supernova progenitors remains only partially settled. The single degenerate model, in which a white dwarf accretes from a normal companion star, and the double degenerate model, in which two white dwarfs merge, both produce Type Ia, like explosions, but may not produce exactly the same luminosity distribution. If the mix of progenitor types changes with redshift, the standardization could be subtly biased in a way that affects the inferred expansion history. Absolutely no one anticipates that this progenitor uncertainty is large enough to eliminate the dark energy signal or to close the Hubble tension. But it is a known source of systematic uncertainty that future surveys with the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope will measure with much greater statistical power. The Roman Space Telescope in particular is designed to observe Type Ia supernovae in the infrared, where they are better standardized and less affected by dust, giving more precise individual distance estimates. The supernova method, refined over 3 decades from an idea in the 1990s to the primary evidence for dark energy, remains one of the 2 pillars of the Hubble tension. That both pillars are supported by independent systematic corrections, different instruments, different wavelengths, and different teams makes the discrepancy between them all the more remarkable. The expansion rate of the universe directly determines one of the most counterintuitive facts in cosmology: how large the observable universe actually is, and why that size is not simply the distance light has travelled since the Big Bang. The universe is approximately 13.8 billion years old. Light travels at about 186,000 miles per second. You might expect that the farthest thing we could observe would be 13.8 billion light years away, because that is as far as light could have travelled since the Big Bang. But the observable universe has a radius of approximately 46 billion light years, much larger than the naive calculation would suggest. The reason is the expansion of space. When light was emitted by a very distant object billions of years ago, the object was much closer to us than it is today. As the light travelled toward us, the space it was travelling through expanded, stretching the light's wavelength and increasing the effective distance. By the time that light reaches us, the object that emitted it has moved, carried by the expansion of space, to a much greater distance than the light itself has travelled. The comoving distance to the edge of the observable universe, the current position of the most distant objects whose light has had time to reach us, is about 46 billion light years in every direction. Beyond that boundary, there is more universe, but light from those regions has not yet had time to reach us. As the universe continues to expand, more light will reach us from greater distances, but the expansion is also accelerating, meaning that objects beyond a certain distance are receding from us faster than light can travel, so their light will never reach us no matter how much time passes. This boundary, the Hubble sphere, is the region within which recession velocities are less than the speed of light. It has a radius determined directly by the Hubble constant, roughly 14.4 billion light years given current measurements. Objects inside the Hubble sphere are within causal contact with us. Objects outside it are receding faster than light, so new light they emit today is moving away from us even as it travels toward us, and will never close the distance. A higher Hubble constant means a faster expansion rate, which means a smaller Hubble sphere. A lower Hubble constant means a slower rate and a larger Hubble sphere. The 8% discrepancy between the two measurements of H0 translates to real differences in the calculated size of the region of space that can communicate with us. No one expects the universe to be a different physical size based on which measurement is correct, but the apparent boundary of causal contact shifts and the implied age of the universe also changes. A higher Hubble constant produces a slightly younger universe, while a lower value implies an older one. The Planck measurement, at about 67.4, implies a universe age of approximately 13.8 billion years. The Schu's measurement, at about 73, implies an age of approximately 12.9 billion years, a difference of roughly 900 million years. That difference matters because astronomers have found old stars, specifically the oldest globular cluster stars, with ages estimated between 12.5 and 13.5 billion years. If the universe is only 12.9 billion years old, those stars are close to the universe's age, uncomfortably so. The expansion rate, in other words, is not just a number. It is the clock of the cosmos, the parameter that connects the age of the universe to its current size, to the oldest objects it contains, and to the ultimate horizon beyond which we are permanently cut off from contact. The Hubble constant is not just a measure of how fast the universe is expanding today. It is the key to measuring how old the universe is, and the two competing values give answers that differ by nearly 1 billion years. The age of the universe can be estimated from the Hubble constant using the concept of the Hubble time, which is simply 1 divided by the Hubble constant. If the universe had always been expanding at its current rate, the Hubble time would be the time since everything was in the same place. With the Planck value of the Hubble constant, the Hubble time comes out to roughly 14.4 billion years. With the Schu's value, it comes out to roughly 13.4 billion years. The actual age of the universe is not quite equal to the Hubble time, because the expansion rate has not been constant, but the Hubble time gives a good approximation of the order of magnitude. More precisely, the age depends on how the expansion rate has changed over cosmic history. In the early universe, the expansion was decelerating due to the gravitational pull of the dense matter content. In the last 5 to 6 billion years, the expansion has been accelerating due to dark energy. Accounting for both phases, the Planck cosmology gives an age of approximately 13.8 billion years, while the Schu's cosmology gives approximately 12.9 billion years. This difference of nearly 900 million years becomes important when you compare it to the ages of the oldest objects we can observe, the globular clusters. Globular clusters are spherical systems of hundreds of thousands to millions of stars, all formed at approximately the same time from the same cloud of primordial gas. They are among the oldest structures in any galaxy. The stars in a globular cluster can be aged using stellar evolution theory. When stars exhaust the hydrogen in their cores, they leave the main sequence, expanding and cooling to become red giants. The brightness at which stars in a globular cluster begin to leave the main sequence, called the main sequence turn-off point, depends on how old the cluster is. Older clusters have a lower, dimmer turn-off point because only the lower, mass, slower burning stars are still on the main sequence. By comparing the observed main sequence turn-off to the predictions of stellar evolution models, astronomers can estimate the age of a globular cluster with an uncertainty of roughly 1 billion years. The oldest globular clusters in the Milky Way halo, which include NGC 6752, NGC 6397, and the famous Methuselah stars host cluster, have ages estimated at between 12.5 and 13.5 billion years. Some individual measurements push toward 13.8 billion years, near the age of the universe in the Planck cosmology. This creates a genuine constraint. The stars in a globular cluster cannot be older than the universe itself. If the universe is only 12.9 billion years old, and some globular clusters are measured at 13 to 14 billion years, the numbers do not add up. The age estimates for globular clusters have significant uncertainties due to uncertainties in stellar physics, specifically in how models treat convection and helium abundance, but the oldest cluster ages are uncomfortably close to or beyond the universe's age in the higher H0 cosmology. No one predicts that the globular cluster age problem definitively rules out the high Hubble constant. The ages of the oldest clusters could be somewhat overestimated due to systematic effects in the stellar models. The Shoes team and others have argued that the age problem is not severe enough to rule out the 45 miles per second per megaparsec cosmology. But it is another piece of the puzzle, another indicator that the two measurements of the Hubble constant are pointing to a tension that has consequences throughout the observable universe. The Gaia satellite is making significant contributions here. By measuring parallaxes to nearby stars with extreme precision, Gaia is improving the calibration of the stellar distance scale, which feeds into the luminosity calibrations used in globular cluster age determinations. With better distances, the ages of individual stars in globular clusters can be pinned down more precisely, reducing the uncertainty that currently blurs the comparison with the age of the universe. There is also a method for measuring the age of the universe that is independent of the Hubble constant. The age of the oldest white dwarfs in globular clusters. White dwarfs cool predictably over time, and the faintest, coolest white dwarfs in a cluster give a minimum age for the cluster. Observations with the Hubble Space Telescope and more recently, with Webb have pushed white dwarf cooling sequences deeper in nearby clusters, giving ages consistent with the stellar turn-off estimates. The age of the universe is one of those numbers that sounds dry and abstract at first, until you stop and realize what it actually means. Every structure in the cosmos, every galaxy, every star, every planet, every atom in the bodies of every organism that has ever lived, formed within that window. The Hubble constant sets the length of that window, and getting it right matters in exactly the same way that getting the scale of the universe right matters. One measurement says we have 13.8 billion years to account for. The other says we have 12.9. Which universe we live in changes the story of how everything around us came to be. Beyond the Cepheid, supernova distance ladder and the cosmic microwave background, there is a third major probe of the Hubble constant that occupies an intermediate position between the early universe and late universe measurements. Baryon acoustic oscillations, or BAO. The same sound waves that imprinted the pattern of fluctuations on the cosmic microwave background also left a signature in the distribution of matter at later times. As the primordial plasma oscillated, the sound waves alternately compressed and rarefied the matter at different scales. When the universe became transparent and the oscillations froze, the matter was left with a preferred clustering scale. Pairs of galaxies are slightly more likely to be separated by about 490 million light years than by nearby distances. This preferred scale is called the BAO scale, or the acoustic scale, and it corresponds to the distance the sound waves travelled before the universe froze. Because the BAO scale is set by physics in the early universe that is well understood and well measured by the CMB, it serves as a standard ruler. Unlike standard candles, which use brightness to infer distance, a standard ruler uses angular size. By measuring the angle that the BAO scale subtends at various distances, and comparing it to the known physical size of the scale, astronomers can measure distances across the universe. The BO scale has been measured in multiple galaxy surveys at different redshifts. The 2 Degree Field Galaxy Redshift Survey first detected it in 2005. The Sloan Digital Sky Survey and its successor, the Baryon Oscillation Spectroscopic Survey BOSS, have since measured it with high precision across a range of redshifts from 0.1 to about 2. The DESI collaboration, using the Dark Energy Spectroscopic Instrument at Kitt Peak National Observatory in Arizona, has produced the most precise BAO measurements to date, released in 2024, based on a survey of tens of millions of galaxies. The BAO measurements are significant for the Hubble tension because they are relatively insensitive to the detailed physics of the distance ladder, but they are sensitive to the sound horizon scale derived from the early universe. If you take the sound horizon value from the CMB measurement, the BAO distances are consistent with a Hubble constant of about 68, aligned with Planck. If you want the BAO measurements to be consistent with a Hubble constant of 73, this sound horizon would have to be smaller than the CMB model predicts. This is actually useful information. It tells us that whatever new physics might explain the Hubble tension, it must change the sound horizon, not just modify the late universe expansion history. Models that only change dark energy behavior after the CMB epoch do not help, because they do not affect the sound horizon that BAO measurements are sensitive to. The new physics must operate at or before recombination. The 2024 DESI BAO results added an interesting wrinkle. When combined with CMB data and Type Ia supernova data, the DESI BAO measurements showed hints that dark energy might not be a simple cosmological constant, but might instead be evolving in a way that is stronger in the past and weaker today. This is still at a relatively low statistical significance, a bit over 2 sigma, meaning it requires confirmation from more data, but it is the first tentative evidence from BAO data that the dark energy model may need refinement. The surface brightness fluctuation method offers yet another independent late universe measurement. Elliptical galaxies have a characteristic graininess in their surface brightness that depends on the number of stars contributing to the image. A closer galaxy appears grainier because individual star clusters can be partially resolved, while a more distant galaxy appears smoother. By calibrating this graininess in nearby galaxies whose distances are known from Cepheids, astronomers can use surface brightness fluctuations to measure distances to elliptical galaxies tens or hundreds of millions of light years away. Recent SBF measurements by John Blakesley and collaborators give Hubble constant values around 73, consistent with the SHOES team. Another independent method uses the Tully-Fisher relation, which connects the rotation speed of a spiral galaxy to its intrinsic luminosity. Faster, rotating galaxies are more luminous. By measuring rotation speeds from the width of the 21 centimeter hydrogen emission line and comparing inferred luminosities to apparent brightness, distances can be measured without any Cepheid calibration steps. Tully-Fisher measurements give Hubble constants that generally land in the 73-76 range. The picture that emerges is striking. Every measurement of the Hubble constant that probes the late universe after the CMB epoch gives values clustered around 73. Every measurement that derives its value from the early universe physics gives values around 67. The boundary between these two regimes, the physics that connects the early universe to the late universe, is where the discrepancy lives. Something that happened between 380,000 years after the Big Bang, and today is not captured by the standard model. By the end of tonight, we want to understand what physics might explain the tension without breaking everything else. If the Hubble tension is real, meaning if neither the CMB measurement nor the local distance ladder measurement contains a significant systematic error, then something in our model of the universe is wrong. Physicists have proposed a wide range of possible fixes, and understanding them gives us a clearer picture of what the universe might be hiding. The most straightforward solutions involve changing what happened in the early universe between the Big Bang and the formation of the cosmic microwave background. The current model gives a specific value for the sound horizon, the distance that sound waves travelled in the primordial plasma before it froze, which sets the scale of the CMB fluctuation pattern. If the sound horizon was smaller than the model predicts, the same CMB pattern would fit with a higher Hubble constant. A smaller sound horizon means the sound waves did not travel as far, which can be achieved by changing the speed of sound in the early universe, or by changing the amount of time between the Big Bang and recombination. One mechanism that has received significant attention is early dark energy. In this proposal, a brief episode of dark energy existed in the early universe, around the time of matter radiation equality, roughly 50,000 years after the Big Bang. This early dark energy would have added energy to the universe at that epoch, speeding the expansion slightly and reducing the time available for sound waves to propagate, which would reduce the sound horizon. With a smaller sound horizon, the CMB pattern fits a higher Hubble constant more naturally. The problem with early dark energy proposals is that they tend to create new tensions with other measurements, particularly with observations of the large-scale structure of the universe, the clustering of galaxies measured by surveys like the Dark Energy Survey and the Baryon Oscillation Spectroscopic Survey. A modified early universe changes not just the CMB pattern, but also the way matter clumped together over cosmic time, and current galaxy clustering measurements are consistent with the standard model rather than with early dark energy variants. Another class of solutions involves modifying the behavior of dark matter. If dark matter were not perfectly cold and collisionless, as the standard model assumes, but had some small interaction rate or some thermal velocity, the pattern of early universe evolution would change in ways that might push the derived Hubble constant upward. Interacting dark matter models, interacting dark matter models, and warm dark matter models have all been explored in the context of the Hubble tension. Modified gravity theories offer another approach. General relativity is the foundation of standard cosmology, but there is no experimental evidence that confirms it on cosmological scales. Theories that modify gravity's behavior at very large distances or very late times could alter the expansion history in ways that change the relationship between the early universe CMB prediction and the late universe local measurement. Some modified gravity proposals predict a different relationship between the expansion rate and the growth rate of large-scale structure, which would be testable with future surveys. The gravitational wave standard siren method is particularly important here. When two neutron stars or black holes merge, they produce gravitational waves whose amplitude depends on the intrinsic energy of the merger, which can be calculated from the waveform. If the electromagnetic counterpart of the merger is also detected, its redshift can be measured. Combining the distance from the gravitational wave amplitude with the redshift from the optical counterpart gives the Hubble constant without using any rungs of the distance ladder and without assuming any cosmological model. The first such measurement came from GW Abasu 17087, the neutron star merger detected by LIGO and Virgo in August 2017. The measurement gave a Hubble constant of approximately 44 miles per second per megaparsec, with an uncertainty large enough to be consistent with both the Planck and Schu's values. As more gravitational wave mergers are detected, and their Hubble constant contributions are averaged, this method should become precise enough to discriminate between the two values. No one predicts it will definitively resolve the tension in the next few years, but by the 2030s, when the Einstein telescope and the Cosmic Explorer are expected to be operational, gravitational wave Hubble constant measurements may become more precise than either the CMB or the local distance ladder. The answer to which solution is correct, if any of the current proposals are, is not known. What is known is that the standard cosmological model, which has been spectacularly successful at explaining a wide range of observations, appears to have a crack in it. The Hubble tension is that crack, and the physics community is taking it seriously enough that it has generated hundreds of papers per year and dozens of proposed solutions, none of which yet cleanly explains the discrepancy without creating problems elsewhere. That pattern is not what you see when a tension is a measurement artifact. It is what you see when the tension is real. Dark energy is the name we have given to whatever is driving the accelerating expansion of the universe, and it is worth examining what that name conceals, because the list of things we do not know about dark energy is far longer than the list of things we do. What we know, something is causing the expansion of space to accelerate. The acceleration has been ongoing since roughly 5 to 6 billion years ago, when the universe was about half its current age. Before that, the expansion was decelerating, slowed by gravity. After that, dark energy began to dominate over matter and gravity, and the expansion has been accelerating ever since. The total energy budget of the universe today is approximately 60% dark energy, 27% dark matter, and 5% ordinary matter and radiation. What we do not know, what dark energy physically is, whether its density changes over time, why it has the particular value it does, and whether the acceleration will continue, slow down, or increase in the future. The simplest model is the cosmological constant, denoted by the Greek letter lambda, which is why the standard cosmological model is called lambda, CDM. A cosmological constant corresponds to a fixed, non-zero energy density of empty space, a property of spacetime itself rather than of any field or particle. Einstein introduced it in 1917 for the wrong reason, removed it, and it was reinstated by the 1998 supernova observations as the best single-parameter description of the dark energy behavior. The problem with the cosmological constant as a physical explanation is the coincidence problem and the fine-tuning problem. The cosmological constant has the specific value it does, approximately 1.1 times 10 to the power of negative 52 per square meter in SI units, a seemingly arbitrary and extraordinarily small number. Quantum field theory predicts that the vacuum energy of space should be many orders of magnitude larger, anywhere from 40 to 120 orders of magnitude above the observed value depending on the energy scale considered. No one expects this discrepancy to be resolved easily. It is sometimes called the worst prediction in the history of physics. The coincidence problem is separate. Dark energy and matter happen to have similar magnitudes in the current universe, making this a special time in cosmic history. If dark energy is a constant, it has always existed at the same density while matter has diluted away. Why are we living in the brief epoch where both are comparable in magnitude? There is no obvious anthropic or physical explanation. Quintessence is the name given to models in which dark energy is not a constant, but a dynamic field that evolves over time, potentially changing its density and its effect on the expansion. Different quintessence models produce different expansion histories, and some predict that dark energy was stronger in the past and will weaken in the future, or vice versa. The equation of state parameter, denoted W, describes the relationship between the pressure and energy density of dark energy. A cosmological constant has W exactly equal to -1. Quintessence models generally have W varying with time. Values of W less than -1 correspond to what is called phantom energy, which would lead to the Big Rip scenario. The 2024 DECIBO results hinted that W might not be -1 and might be evolving, with a value closer to -0.8 at the present and different in the past. This is the first statistically suggestive evidence from Bayo data that dark energy might be dynamic rather than a simple cosmological constant. The significance is not yet high enough to claim a discovery, but if the trend holds with more data, it would be a fundamental revision of the cosmological constant picture. Dark energy is also connected to the Hubble tension through the possible existence of early dark energy. Early dark energy models propose a second component of dark energy, distinct from the cosmological constant, that was present in the early universe and decayed away after some epoch. This early component would have speeded the early expansion slightly, reducing the sound horizon and thus allowing the CMB measurements to fit a higher value of the Hubble constant. The challenge for early dark energy models is that they tend to change the predicted amplitude of large, scale structure fluctuations in ways that conflict with current observations of galaxy clustering and the matter-power spectrum. The DESI survey and the Dark Energy survey are providing increasingly precise measurements of large-scale structure, and so far those measurements are more consistent with the standard model than with the early dark energy variants. What the dark energy landscape reveals is that the Hubble tension is not an isolated problem. It sits at the intersection of dark energy physics, the physics of the early universe, and the calibration of the late universe distance scale. Any solution to the tension must be consistent with the full body of cosmological observations, and that constraint eliminates most naive proposals quickly. The tension's persistence, despite years of scrutiny and hundreds of proposed solutions, is what gives it its significance. Gravitational wave astronomy offers the most promising pathway to an independent measurement of the Hubble constant that sidesteps every rung of the distance ladder and makes no assumptions about early universe physics. Understanding how this works illuminates both the power of the method and the difficulty of making it precise. Gravitational waves are ripples in spacetime, predicted by Einstein's general relativity in 1916 and first directly detected by the LIGO collaboration on September 14, 2015. The detection was of two merging black holes roughly 1.3 billion light years away. The waves caused mirrors in the LIGO detector, which are separated by 2.5 miles, to move relative to each other by a distance smaller than 1/10,000th the diameter of a proton. For cosmology, the relevant events are mergers that produce electromagnetic counterparts alongside the gravitational wave signal. Binary black hole mergers are invisible in light, but binary neutron star mergers produce an accompanying burst of gamma rays, X rays, optical light, and radio waves as the expelled material is heated and accelerated. Finding that optical counterpart and measuring its redshift gives the merger's recession velocity. The gravitational wave signal gives the distance. The distance comes from the signal's amplitude. Unlike electromagnetic waves, whose intrinsic brightness we must calibrate using complex astrophysics, the intrinsic amplitude of a gravitational wave signal can be calculated from first principles using general relativity if you know the masses and spins of the merging objects. The masses and spins are encoded in the waveform of the signal itself, which can be extracted by matching the observed waveform to a library of theoretical templates. This is why gravitational wave sources are called standard sirens. The intrinsic loudness of the event is calculable from the signal alone, without any calibration chain. The first measurement using this method came from G-Babelsansen 817, a binary neutron star merger detected on August 17, 2017. The accompanying gamma-ray burst was detected by the Fermi satellite 1.7 seconds later. Over the following days, optical telescopes observed the kilonova, the glowing fireball of ejected material, in the galaxy NGC 4993, located about 130 million light, years away in the constellation Hydra. The measured recession velocity of that galaxy, from its optical spectra, was approximately 2,000 miles per second. Combining this with the gravitational wave distance gave a Hubble constant of approximately 44 miles per second per megaparsec, with a fractional uncertainty large enough to be consistent with both the Planck and Schu's values. 70 is right between the two competing values. The uncertainty was too large to discriminate, but one event is not the limit of the method. The precision of the gravitational wave Hubble constant measurement improves approximately as the square root of the number of events used. To achieve 1% precision, which would cleanly distinguish between 67 and 73, cosmologists estimate needing roughly 50 to 100 well-observed binary neutron star mergers with optical counterparts. LIGO, Virgo, and the Kagura detector in Japan observed several dozen gravitational wave events per year during the fourth observing run, which began in May 2023. Not all of these events have optical counterparts. Most are binary black hole mergers. Binary neutron star mergers are rarer, and many occur too far away for the optical counterpart to be easily identified. By 2026, the cumulative catalogue of neutron star mergers with usable redshifts is expected to be in the range of a few to a dozen, giving a gravitational wave Hubble constant with an uncertainty of several percent. The next generation of gravitational wave detectors will transform this picture. The Einstein telescope, proposed for construction in Europe, and the Cosmic Explorer, proposed for the United States, will be sensitive to neutron star mergers throughout the observable universe, detecting thousands of events per year. Combined with systematic optical follow-up programs, these observatories could yield a gravitational wave Hubble constant measured to better than 0.1% precision within a decade of operation, far surpassing either the CMB or the distance ladder in precision. There is also a method called statistical sirens, in which binary black hole mergers, which have no optical counterparts, are used by statistically correlating the gravitational wave distance measurement with the redshifts of all galaxies in the survey volume, weighted by their probability of being the host galaxy. This method is noisier for individual events, but can be applied to every detected merger, eventually building up a statistical Hubble constant from hundreds of binary black hole events. The gravitational wave approach is also immune to the specific sources of systematic error that affect both competing methods. It does not depend on the calibration of Cepheid variables, the standardization of type Ia supernovae, the model of the early universe from which the CMB Hubble constant is derived, or any assumption about dark energy. It is as close to a model-independent distance measurement as exists in cosmology. No one predicts what the gravitational wave Hubble constant will ultimately converge to. That is precisely the point. It is an independent check, and when it reaches sufficient precision to discriminate between 67 and 73, it will either confirm one of the existing measurements and give us a candidate systematic error to find in the other, or it will give a third value, indicating that something more complex is going on. Either result would be significant. The scientific community has specific plans for resolving the Hubble tension, and the instruments being built and launched in the coming decade are well matched to the specific uncertainties in each competing measurement. The Nancy Grace Roman Space Telescope, named for NASA's first chief of astronomy and scheduled for launch in the mid-2020s, is designed in part to directly address the Hubble tension. Roman carries a wide field camera covering 100 times the sky area of Hubble's comparable instrument, allowing it to survey vast numbers of galaxies for type Ia supernovae simultaneously. It observes primarily in the near-infrared, where type Ia supernovae are better standardized and less affected by dust extinction than in visible light. The Roman supernova survey is expected to discover tens of thousands of type Ia supernovae at redshifts between about 0.2 and 2.5, providing a statistical measurement of the expansion history with unprecedented precision. Roman will also improve the Cepheid calibration, observing Cepheids in galaxies that are difficult to study with Hubble's smaller field of view and in the same infrared bands where the period-luminosity relation is most reliable. The combination of better Cepheid calibration and better supernova standardization could reduce the statistical and systematic uncertainties in the local Hubble constant measurement by a factor of several. The Vera Rubin Observatory in Chile, now in commissioning phase, carries the legacy survey of space and time, LSST, which will photograph the entire visible southern sky every few nights for 10 years. Over its operational lifetime, LSST is expected to discover approximately 1 million type Ia supernovae, a sample so large that the limiting factor in Hubble constant measurements will shift entirely from statistics to systematic uncertainties. Understanding and controlling those systematics particularly in the photometric calibration of the survey and the modelling of dust extinction, is a major focus of the LSST science community. The CMB side of the tension also has new experiments underway. The Simons Observatory in Chile and the successor CMB S4 project are building arrays of microwave detectors with much higher sensitivity than the original Planck satellite, focusing on small angular scales, where the CMB power spectrum has features that constrain the Hubble constant through the sound horizon with high precision. These experiments will also measure the effect of gravitational lensing on the CMB, which is sensitive to the total amount of matter between us and the last scattering surface, providing additional constraints on the cosmological model. The Euclid satellite, launched by the European Space Agency in 2023, is conducting a wide field survey of galaxies and weak gravitational lensing across a large fraction of the sky. Euclid's primary goal is to measure dark energy and its behaviour over cosmic time, but it will also provide BAO measurements of exceptional precision and will measure the growth rate of large-scale structure with percent level accuracy. If the Hubble tension reflects new physics in the dark energy sector, Euclid's measurements will be sensitive to that physics. The Dark Energy Spectroscopic Instrument, DESI, operating at Kitt Peak, is conducting the largest spectroscopic galaxy survey ever attempted, measuring precise redshifts for tens of millions of galaxies over a 5-year program. The BAO measurements from DESI have already, as of their 2024 data release, provided the tightest constraints on dark energy behaviour to date and have hinted at evolution in the dark energy equation of state. By the time the full DESI survey is complete around 2027, the BAO constraints will be a factor of several better than anything available before DESI. The gravitational wave avenue is developing rapidly as LIGO, Virgo and CAGRA continue observing runs with improving sensitivity. The fourth observing run, which began in 2023, is detecting gravitational wave events at a rate much higher than earlier runs. The crucial bottleneck for the standard siren Hubble constant measurement is the optical identification of binary neutron star merger counterparts, which requires rapid telescope follow, up within hours of the gravitational wave alert. Programs coordinating space telescopes, wide field-ground telescopes, and radio observatories for rapid follow-up are now mature enough to capture most counterparts when they occur in accessible sky positions. Looking further ahead, the Einstein telescope, a proposed underground third-generation gravitational wave detector in Europe, and the Cosmic Explorer, a proposed 25-mile arm length detector in the United States, would detect binary neutron star mergers to cosmological distances and with much higher signal to noise than current detectors. The Einstein telescope alone is expected to detect hundreds of binary neutron star mergers per year, out to distances of billions of light years, with hundreds having optically identified counterparts. The gravitational wave Hubble constant measurement from this dataset would be the most precise in the history of cosmology. No one expects the Hubble tension to remain unresolved through the 2030s. The data coming from all of these instruments is too precisely targeted at the specific uncertainties in each measurement method. Either the tension will collapse as systematics are identified and corrected, or it will solidify into a confirmed discrepancy that demands a revision of the standard cosmological model. Neither outcome would be unremarkable. A resolution through systematic corrections would represent a triumph of precision science. A confirmed real tension would represent the discovery that the universe contains physics we do not yet understand. Both are outcomes worth the enormous investment in instruments and human effort that is going into measuring one number to better and better precision. Tonight, to understand the deepest context for the Hubble tension, we need to go back to the first fraction of a second of the universe's history, to a period called cosmic inflation, because it sets the initial conditions from which everything we observe today, including the precise pattern of the CMB fluctuations and the large-scale structure of the universe, ultimately evolved. By the end of tonight, the connection between what happened in the first 10 to the power of negative 36 seconds and the measurement discrepancy we are living with today should feel less abstract than it first appears. Cosmic inflation is the hypothesis that the very early universe underwent an extraordinarily rapid, exponential expansion lasting from approximately 10 to the power of negative 36 seconds to 10 to the power of negative 32 seconds after the Big Bang. During this brief episode, the universe expanded by a factor of at least 10 to the power of 26, and possibly much more. To put that in tactile terms, if you took a proton and inflated it by the same factor that inflation inflated the universe, the proton would expand to a sphere larger than the observable universe. This all happened in a period shorter than any human timescale by an almost incomprehensible margin. No one expects inflation to be easy to conceptualize. It was proposed in 1980 by Alan Guth, then a postdoctoral researcher at SLAC National Accelerator Laboratory, as a solution to several problems with the original Big Bang model. 3 problems in particular motivated the proposal. The first is the horizon problem. The cosmic microwave background is nearly identical in temperature in every direction we look, to within 1 part in 100,000. But the regions of the universe that produce the CMB in opposite directions in the sky were, at the time of recombination, so far apart that they could never have exchanged light or heat in the 380,000 years since the Big Bang. There was no time for them to reach the same temperature, yet they are the same temperature. Without inflation, this is inexplicable. With inflation, it is natural. All of the CMB we observe was once an extraordinarily tiny, causally connected region, that inflation then blew up to the scale of the observable universe. The second is the flatness problem. The universe, as measured by the geometry of space on the largest scales, is geometrically flat to very high precision. Flatness is an unstable condition in standard Big Bang cosmology. The universe will move away from perfect flatness as it evolves, meaning that the early universe would have had to be tuned to flatness with extreme precision to still be flat today. Inflation drives the universe toward flatness during the exponential expansion, making the observed flatness a natural outcome rather than an improbable coincidence. The third problem is the absence of magnetic monopoles. Some grand unified theories of particle physics predict that exotic particles called magnetic monopoles should have been produced in huge numbers in the early hot universe. But no magnetic monopole has ever been detected. Inflation solves this by diluting any monopoles produced before inflation to a density so low that we would not expect to find one in the observable universe. Inflation also provides the mechanism for generating the primordial density fluctuations that seeded all structure in the universe. During inflation, quantum mechanical fluctuations in the inflaton field, the quantum field driving the inflation, were stretched to macroscopic scales by the exponential expansion. These fluctuations became the density variations in the early universe, the seeds from which galaxies, clusters, and all large-scale structure grew. The specific statistical properties of these fluctuations, called the primordial power spectrum, are imprinted in the pattern of CMB temperature fluctuations that Planck measured so precisely. Here is where inflation connects to the Hubble tension. The inflaton field, whatever it is, must have had specific properties that determined how long inflation lasted and what spectrum of fluctuations it produced. Some models of inflation predict that the inflaton field had a non-trivial behavior near the end of inflation, or in the transition from inflation to the hot Big Bang that followed. If there was additional energy in some field that was active in the early universe before recombination, that energy could have affected the expansion rate during the epoch when the CMB acoustic oscillations were propagating. Early dark energy models are in a sense postulating a new field that was active in the universe at the epoch of matter, radiation equality, analogous to the inflaton but operating much later and at lower energy scales. The motivation from the Hubble tension side is straightforward. If this field existed and contributed meaningfully to the energy budget around redshift 3000 to 10,000, before recombination, it would reduce the sound horizon and allow the CMB to be fit with a higher Hubble constant. The connection to inflation is more speculative but worth noting. Some researchers have explored whether the initial condition set by inflation could have left a non-trivial imprint on the transition to the hot Big Bang, producing an effective early dark energy component as a natural consequence of the inflationary dynamics. If such a connection exists, the Hubble tension might ultimately be teaching us something about the physics of inflation itself, the very first moments of cosmic history. This is speculative, but speculation is the appropriate mode when the data produces a persistent anomaly for which no conventional explanation works. The Hubble tension sits at the edge of what our current model can explain, and the edges of models are where the most interesting physics lives. The possibility that measuring the universe's current expansion rate might reveal something about what happened in the first tiny fractions of a second is an example of how the cosmos hides its deepest secrets in unexpected places. The Hubble constant, at first glance a simple description of how fast things are moving apart, turns out to be a probe of the entire history of the universe from its first moments to today. Tonight, we should step back from the technical details and think about what the Hubble tension actually means for how we understand our place in the universe. The standard cosmological model, lambda CDM, is one of the most precisely tested scientific theories ever developed. It successfully explains the pattern of CMB fluctuations, the abundances of light elements produced in the first few minutes after the Big Bang, the large-scale distribution of galaxies across the observable universe, the observed acceleration of the expansion, and dozens of other observations spanning 13 orders of magnitude in physical scale. It makes specific, quantitative predictions that have been confirmed by multiple independent experiments. For most of the last 3 decades, it has felt like a finished theory, or nearly so. The Hubble tension has changed that feeling. Not because any single measurement is wrong, but because 2 high, precision measurements with independent methodologies, both carefully calibrated and scrutinized by teams on both sides, give answers that differ by a statistically significant amount. At 5 sigma, this is not a number to dismiss. It is a signal. By the end of tonight, we will understand that what that signal might mean is not that we have been wrong about everything, but that our model has a gap. Something is missing. Some element of the universe's physics is not captured by the combination of a cosmological constant, cold, dark matter, ordinary matter, and the standard inflationary initial conditions. The universe is more complicated or more interesting than the current standard model suggests. This is not unprecedented in the history of physics. The history of science is in large part a history of models that were spectacularly successful until a precise enough measurement revealed a discrepancy that forced a revision. Newton's mechanics was extraordinarily successful for over 2 centuries, until precise observations of Mercury's orbital precession and the behavior of light near massive objects revealed that it needed to be replaced by general relativity. The ultraviolet catastrophe in black-body radiation, which seemed like a minor technical problem in the late 19th century, led to the discovery of quantum mechanics. The apparent instability of the atom in classical electrodynamics led to the same revolution. In each of those cases, the discrepancy that forced the revision was not large in absolute terms. Mercury's orbital precession was a small effect, tiny compared to the total orbital motion. The black-body spectrum problem seemed like computational detail, not a fundamental crisis. The Hubble tension, at 8%, is similar in character. It is not a catastrophic disagreement, but it is large enough to be real and small enough to be subtle, which means whatever explains it is probably a refinement of the existing framework rather than a replacement of it. No one expects the resolution to be simple. If it were simple, someone would have found it already. The fact that hundreds of researchers have proposed solutions and none has survived without creating other problems elsewhere suggests that the resolution is genuinely non-trivial, that it requires new ideas rather than just better calculations of known physics. What might that new physics be? The candidates include early dark energy, some variation of dark matter that behaves differently at early times, a neutrino physics beyond the standard model, modifications to general relativity on cosmological scales, or something more exotic that has not yet been imagined. The new physics must be subtle enough not to disturb the many other predictions of lambda, CDM that work correctly. It must specifically alter the relationship between the early universe sound horizon and the late universe expansion rate, because that is exactly where the discrepancy lives. One of the most striking features of the Hubble tension is how it resembles other moments in physics when measurements on very different scales produced an unexpected discrepancy. The rotation curves of galaxies, which showed that stars at the outer edges of galaxies orbit faster than the visible matter can account for, revealed the existence of dark matter. The brightness of type Ia supernovae at high redshift revealed dark energy. Both of those discoveries came from measurements that disagreed with the predictions of, established theories in ways that could not be explained by systematic errors. The Hubble tension has the same character. The most honest interpretation is this: we have built a remarkably accurate model of the universe. That model makes specific predictions about the relationship between the early universe and the late universe. The measurements of those predictions do not quite agree. We do not know why. And that gap in our knowledge, that honest admission of a 5 sigma discrepancy between two precisely calibrated measurement methodologies, is where the next chapter of cosmology begins. No one predicts which chapter it will be. It might be the chapter of early dark energy. It might be the chapter of modified neutrino physics. It might be the chapter of a third, completely independent measurement that lands between the two existing values and helps identify which systematic error is large enough to close the gap, or confirms that no systematic error is large enough and the new physics is real. We are living through the early pages of whatever chapter comes next. The universe, as best as we can tell, is between 12.9 and 13.8 billion years old. It is between 42 and 45 miles per second per megaparsec in its current expansion rate. And in the gap between those two values, there may be something we have not imagined yet, waiting to be found by the people who are building the next generation of telescopes and detectors and ideas. The expansion of the universe does not reach into our immediate cosmic neighborhood. The Milky Way and Andromeda are not flying apart. Neither are the dozen or so smaller galaxies that make up our local group. Gravity, at the scale of galaxy groups and galaxy clusters, is strong enough to hold structures together against the expansion of space. Understanding where expansion takes over and where gravity wins is essential for interpreting Hubble constant measurements and for understanding what the night sky will look like in the deep future. The boundary at which gravity and expansion are in rough equilibrium is called the zero-velocity surface of a structure. For the local group, this boundary lies at roughly 3 to 4 million light years from the center of mass of the group. Galaxies within this boundary are gravitationally bound to the local group and will remain associated with it indefinitely, even as the rest of the universe expands away. Galaxies beyond this boundary are receding, carried by the Hubble flow. The Andromeda Galaxy and the Milky Way are, in fact, moving toward each other. Despite being part of an expanding universe, the gravitational attraction between our two galaxies is stronger than the expansion that would otherwise push them apart at their separation of about 2.5 million light years. The two galaxies are approaching at roughly 70 miles per second along the line connecting them, though with a substantial transverse component that makes the collision geometry uncertain. Current models predict that the Milky Way and Andromeda will undergo a gravitational interaction, probably a first close pass, in roughly 4 to 5 billion years, followed by a merger that will complete over the following several billion years. The merged galaxy, sometimes called Milkomeda in informal usage, will be an elliptical or lenticular galaxy, with a very different structure than either of its progenitors. the Sun is expected to survive the merger, though it may be displaced to a very different location in the resulting galaxy. The night sky during the merger, billions of years from now, would be spectacular and strange, with the stars of Andromeda spread across a band across the sky in a display unimaginable from our current perspective. The local group as a whole is embedded in the Virgo supercluster, a larger concentration of galaxy groups and clusters extending roughly 100 million light years in every direction. The Virgo supercluster is not bound. It will not collapse into a single structure. The expansion of space will eventually pull its constituent groups apart, leaving each group isolated in an increasingly empty void. On timescales of tens of billions of years, the local group will be an island universe in a nearly empty cosmos, its nearest neighbours having receded beyond the cosmological event horizon. The Laniakea supercluster, an even larger structure mapped by Tully and collaborators in 2014 using peculiar velocity data, encompasses a volume of space roughly 500 million light years across and contains our local group as a small constituent. Laniakea is also not bound in the usual gravitational sense. It is a flow pattern, a region of space where the peculiar velocities are all directed toward a common point, a concentration of mass sometimes called the great attractor. But because of dark energy's acceleration of the expansion, the outer parts of Laniakea are already being torn away by the expansion, and the structure will not persist as a coherent entity indefinitely. This picture of bound versus unbound structures matters for Hubble constant measurements, because the transition between bound and expanding regions is where peculiar velocities are largest, and where naive Hubble flow measurements are most contaminated. A galaxy near the boundary of a supercluster might have a peculiar velocity of several hundred miles per second directed toward the cluster's centre, which would significantly contaminate any Hubble constant estimate based on that galaxy's recession velocity. The large-scale flow of galaxies toward the Shapley supercluster, the largest concentration of mass in the nearby universe, has been measured using peculiar velocity surveys and found to be consistent with the Standard Model's predictions of how matter clusters under gravity. This is one area where peculiar velocity measurements actually support the Standard Model rather than adding tension. The amplitude of the flows, the speed at which galaxies are falling toward mass concentrations, agrees with the lambda CDM prediction. If anything, peculiar velocity measurements provide some support for the lower Planck value of the Hubble constant, because a higher Hubble constant would produce slightly different predictions for the growth of structure and the amplitude of peculiar velocities. No one expects the boundary between bound structures and the expanding universe to be perfectly sharp. At the scale of galaxy groups, the zero-velocity surface is a spherical shell, but with local perturbations due to the irregular mass distribution of the group. The Milky Way's zero-velocity surface, for instance, is not a perfect sphere, but is deformed by the gravitational influence of the Virgo cluster to the north. Understanding the relationship between the expansion of space, the gravitational clustering of matter, and the large-scale flow of galaxies requires a consistent cosmological model. The Hubble constant is the foundation of that model. It sets the rate at which the universe is expanding today, which in turn determines how strongly dark energy is pushing space apart at every scale, from superclusters down to galaxy groups. Measuring it precisely is not an academic exercise. It is the key to understanding the dynamics of everything from our cosmic neighbourhood to the farthest reaches of the observable universe. Tonight we have spent time measuring the present, but the expansion rate also determines the eventual fate of everything that exists, and the different scenarios play out in ways that range from the gradual and cold to the violent and absolute. By the end of tonight, we want to hold all of that in mind. The outcome depends on two things: the expansion rate itself and the nature of dark energy. If dark energy is exactly a cosmological constant, a fixed energy density that does not change over time, the expansion will continue accelerating forever at its current pace. gravity will hold bound structures together, the local group of galaxies will remain as a unit, but everything beyond it will recede until it falls below the observable horizon. Over many billions of years, the stars within our galaxy will exhaust their fuel and burn out. After hundreds of trillions of years, the last stars will cool and go dark. After stupendously longer periods, the remaining matter will decay, and the universe will approach a state of maximum entropy, an increasingly cold, dark, and uniform expanse with virtually no structure remaining. This scenario is called the Big Freeze, or the heat death of the universe. It is considered the most likely outcome under the current cosmological model. But dark energy might not be a cosmological constant. If it is a dynamic field that grows in strength over time, the expansion could accelerate faster and faster, eventually reaching a rate at which the expansion overcomes not just the gravity holding galaxy clusters together, but the forces holding individual galaxies, solar systems, planets, and ultimately atoms together. In that scenario, called the Big Rip, every structure in the universe is eventually torn apart by the accelerating expansion, ending in a finite time that depends on the rate at which dark energy grows. Some models place the Big Rip tens of billions of years in the future. Others suggest it may not happen at all. There is also a more exotic possibility. Dark energy could fade or even become repulsive in the future, allowing gravity to eventually dominate and slow the expansion back to a halt, then reverse it. In that scenario, called the Big Crunch, the universe collapses back into itself, mirroring the compression that preceded the Big Bang but in reverse. Current observations strongly disfavor this scenario, but the nature of dark energy is not well enough understood to rule it out completely. Which of these fates awaits the universe depends on the precise behavior of dark energy, which current measurements cannot pin down with confidence. The Hubble tension is part of this picture, because a universe that is expanding faster than the Planck model predicts may have a dark energy component that is slightly different from a simple cosmological constant. If the tension reflects real new physics, it could be an early signal of the mechanism that ultimately determines which of these endings the universe moves toward. No one predicts that resolving the Hubble tension will tell us exactly how the universe ends. But it would narrow the range of possibilities, eliminate some dark energy models, and potentially point toward the kind of physics that governs the larger scales of the cosmos across its entire history. What we can say with confidence is that the expansion, whatever its ultimate trajectory, is the dominant fact about the large-scale structure of the universe. The clustering of galaxies, the distribution of matter, the temperature of the cosmic microwave background, the age of the oldest stars, and the distance to the farthest objects we can observe are all expressions of a universe that emerged from a hot, dense state and has been expanding and cooling ever since. The Hubble constant is the single number that ties all of those observations together into a coherent picture. Getting it right is not an academic exercise. It is the foundation on which cosmology stands. We began tonight with a number, somewhere between 67 and 73. We end with something more interesting than a number, which is the recognition that the uncertainty in that number is not a failure of measurement. It is a signal. There is a specific thing that happens when you hold the full picture of the Hubble tension together. The Cepheid variables measured by the SHOES team, calibrated with geometric parallaxes from Gaia and independent binary star measurements, giving approximately 45 miles per second per megaparsec. The cosmic microwave background, mapped across the entire sky by Planck with temperature sensitivity of 1 part in 100,000, giving approximately 42. The gravitational wave standard siren from the neutron star merger in NGC 4993, landing near 44, with uncertainty still large enough to be consistent with both camps. The gravitational lensing time delays from Herlikau and TD Cosmo, aligning with the local value. The surface brightness fluctuations also aligning with the local value. The baryon acoustic oscillations from DESI, aligning with the early universe anchor. the JWST Cepheid measurement, confirming the local distance ladder rather than resolving it downward. All of those measurements, from all of those methods, from all of those instruments, are sitting at opposite ends of that 8% gap, and the gap has not closed as measurements have improved. It has sharpened. No one expects a discrepancy at 5 sigma, with this breadth of independent confirmation on both sides, to simply evaporate under further examination. Measurement artifacts tend to shrink as you apply more scrutiny. Real physical signals tend to persist. The Hubble tension has been scrutinized for a decade by teams on both sides of the debate, with every systematic error they could think of, and the gap remains. What that means is that one of the most carefully constructed models in the history of science, the lambda CDM cosmological model, has a crack in it. The model was built to explain what the universe looks like at the earliest observable times and what it looks like now, and it does both extraordinarily well, with the exception of this one parameter. The universe is expanding at a rate that the model does not fully account for. The most honest answer to the question we started with, how fast is the universe actually expanding right now, is this: we do not know with the precision we thought we did. And the reason we do not know may be telling us something important about the physics we are missing. We think the universe is expanding at somewhere between 42 and 45 miles per second per megaparsec, a disagreement of roughly 8% that has refused to close despite a decade of scrutiny. We know that means the most distant galaxies we can see are receding from us at 2 or 3 times the speed of light, not by breaking any physical law, but by riding the stretching of space itself. We know that the expansion is accelerating, driven by something we have named dark energy and do not deeply understand. We know that the accelerating expansion will continue, that galaxies now visible to us will eventually cross the horizon of causal contact and be permanently inaccessible, and that the long-term future of the universe is cold and dark and increasingly silent. But within that broad picture, the specific rate matters. It matters for the age of the universe. It matters for the size of the observable region. It matters for what dark energy is doing and will do. It matters for whether a new generation of detectors and telescopes will need to revise the model that has guided cosmology for 3 decades. The resolution may come from the Einstein telescope or the Cosmic Explorer, measuring dozens of gravitational wave standard sirens to percent, level precision. It may come from DESI, accumulating galaxy spectra that push the BAO measurement to unprecedented precision. It may come from the Vera Rubin Observatory, cataloguing hundreds of thousands of Type Ia supernovae and finally testing the supernova standardization at the level of detail needed to find a subtle systematic error. It may come from Webb, measuring Cepheids in environments we have not yet surveyed, in galaxies more representative of the supernova host population. Or it may not come from any of those. It may require a theoretical insight that changes how we model the physics between the Big Bang and today, an extension of lambda, CDM that accommodates new early universe physics without breaking everything the model already explained successfully. No one predicts exactly how this will unfold or when. That is not a failure of cosmology. It is cosmology doing what science does when it finds something real, not collapsing, but expanding its inquiry to match the size of the problem. Something in that picture, in that careful accumulation of measurements from a dozen different methods using different physics, different wavelengths, and different instruments, is telling us something the current model cannot quite account for. And the people paying attention to it, the people who refuse to dismiss the 8% gap as a calibration error, may be the ones who lead us toward the next version of our understanding of the cosmos. We are measuring the expansion of the universe with more precision than any generation of scientists before us, and we have found, in doing so, that the universe is not quite as predictable as our best model suggests. And that discovery, the discovery that the cosmos has more to teach us, is the one that matters most. Sleep well tonight. The universe is still expanding, we are still measuring, and the answer, when it comes, will almost certainly surprise us. Good night.